So these things we call inverse functions, they become quite important in a lot of the things we end up doing. The symbol we use for inverse functions, now be very careful, it is the -1, but it does not mean to the power of -1. It's not like a reciprocal, which is what power of -1 is. So we go F and we just use that symbol of -1. You might have noticed it on your calculators with the trig. Make sure, hang on, let's see this one. Yeah, you see above the sine button and the cos button and the tan button, you got cos with a -1, sine with a -1, and so on. That's the one where you want to find the angle rather than the ratio, and you go shift that button. It's doing the inverse, it's going back the other way, it's finding the angle. If you were to create a composite function using the function and its inverse, doesn't matter which way round you do it, sub the inverse into the function or the function into the inverse, you will get the answer x, because inverses cancel each other out. Right? The addition and subtraction. If you add a number, then subtract the number, you're back to where you started. Multiplication and division. Multiply a number, divide. Back to where you started. And that's what these functions do. It sends the range back to the domain, back to where we started. They were equal sets. Let's do this one as an example. There's my original function, x minus 2 on x plus 2. I'll just work out what the inverse is. Swap the x and y's around. A little bit of work here to do to make y the subject, but play around with the algebra and I come up with this one. Y equals 2x plus 2 on 1 minus x. Okay, what should happen is I can substitute either one into the other and it will get x. So first of all, I'm going to substitute in function x into the inverse. So function x going into the inverse function. Everywhere I see x, I'm replacing with x minus 2 on x plus 2. Fractions on fractions, so the first thing I'm going to do is multiply everything by x plus 2, get rid of that, tidy up the algebra. I've got 4x on foot, which is x, what I was expecting. Do it the other way, let's see. If I was to substitute that inverse into the function itself. So now, everywhere I see an x in function x, I'm going to sub in 2x plus 2 on 1 minus x. Same deal, denominator's the same, so let's multiply by 1 minus x, play around with the algebra, and again we get x. So that's confirming that, yeah, we got an inverse function here, this works. So how do you find the domain and range of an inverse? Remember we said domain and range swap around? So if the point AB is on the function, then the point BA should be on the inverse function. The x and y's are swapped around. And so the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. Okay. Exponential, I've got e to the power of x. There it is, our exponential curve. We know it has a y-intercept of 1. Domain, all real x. Range, y is greater than 0. Swap the x and y's around. Now, remember our log laws and that? Well, I can rewrite this exponential. How do you undo an exponential? You log both sides. We'd end up with y equals the log of x. The log of x has a domain of x is greater than 0. I know that now because the range swaps with the domain. And the range will become all real y because the domain of the exponential was all real x. In fact, if I was to draw it, it should be a reflection in y equals x. And hopefully you recognise that red one. Yeah, that is what we recognise to be a log curve. So there are the inverses of each other. Thing is, not a lot of functions have inverse functions. You're only ever going to have ones that are continually increasing or continually decreasing. In other words, they never turn and come back on themselves. Because as soon as it comes back on itself, it's going to fail the horizontal line test. That makes it very limiting on what we can do. So what we tend up doing is restricting the domain of the function so that we can create an inverse. But it will only work for this restricted domain. So any function can be made invertible by restricting it so it becomes one-to-one. We want to get a piece of the curve that is either continually increasing or continually decreasing. That's what we want to try and do. Okay. Let's go back to our parabola. There it is, y equals x squared. Fails the horizontal line test, no good. At the moment, its domain is all real x and the range is y is greater than or equal to 0, but as I say, hasn't got an inverse. We need to get a piece of that parabola, which is continually increasing or continually decreasing, and ends up getting the range. If we can, I've got two choices here. I could go from 0 all the way to infinity. That would get the complete range. It would be the same. Or of course I could go from minus infinity to 0 as well. So I do have a choice. We tend to go with the positives if possible. So I'm going to restrict it, x is greater than or equal to 0. The range will still be y is greater than or equal to 0. I was able to capture the whole range. That wasn't a problem. What is the function? And notice I'm using index notation here rather than using the square root symbol. But it'll be x to the power of a half. In other words, the positive square root. If I was to draw it, there it is. It's just the top half of the parabola. So y equals the square root. That's the inverse function, not the complete sideways parabola. This then gives us another way of finding the range of a function. Because it might be easier, not always, but it might be easier to find the domain of the inverse function. Because remember when you did domain and range, that the domain, that sometimes proved easier to find than the range. So if I can go and find the domain of the inverse function, then I know, well, that's going to be the range of the original function. Again, let's look at y equals x squared. I don't know what this picture looks like. Let's just imagine that. I've changed it to capital X and capital Y so I don't get confused. So we've swapped the x and the y's round, but I've made it capital X and capital Y so I know which one's the inverse function here and which one's the original one. Well, that became y equals the square root of x. Now I can easily find the domain of that because I know I can't find the square root of a negative number. So the domain of this new function, the inverse function, is x is greater than or equal to 0. So that is telling me that the range of the original function must have been y is greater than or equal to 0. That gives us another way of doing it. X squared plus 3 then. Swap the x and the y's around again. I'll make them capitals so I don't get confused. Let's make y the subject and I get the square root of x minus 3. Hang on, that means the domain of this new function is x is greater than or equal to 3. So the range of that original function must have been y is greater than or equal to 3. Absolute value of x plus 2 minus 5. Swap the x and the y's around. I've got to make y the subject of this. This is a bit trickier, but I'm going to get x plus 5 is the absolute value of y plus 2. Well, that tells me that x plus 5 must be greater than or equal to 0 because it's equal to the absolute value of something. So the domain of the new function, x is greater than or equal to negative 5, which tells me the range of the original function was y is greater than or equal to negative 5. Ooh, this square root y. Square root of 4 minus x squared. Swap the x and the y's. Let's try and make y the subject of this. And I end up with y is the square root of 4 minus x squared. This is where I got to be careful. See, the domain of the new function is minus 2 to 2. But when I go back to the original function, I know that's not going to work for the range because it's the positive square root. I can't get negative numbers. So the actual range of the original function is not in between minus 2 and 2 this time. It's only going from 0 to 2. I can't get negative numbers. So it's not a 100% foolproof way of doing it. Sometimes we have to use other information to get it. But for some of them, yeah, it gives us a great way of finding it. What about this one? Y equals x plus 7 on x plus 4. Swap the x and the y's around. Let's make y the subject. A bit of manipulation there, but I can get it. We end up with 7 minus 4x on x minus 1. Well, the domain of that one is all real x except x equals 1. And this one, yeah, that works fine. All real y, except y equals 1 would be the range of the original function. Okay, that'll do us. 5G.